Another way of having qualitative analysis is what is called phase plane analysis. You transform an ODE into a system of ODEs. We have already seen it some time ago. There was this example with the third derivative of y being transformed into an ODE system with various elements in the matrix A, the matrix A being not a constant. We can do something very similar in our previous example. We're going to introduce y being the derivative of x. Then we have a system of ODEs, two-dimensional, in which x prime is equal to y and y prime is equal to a term that is the rewriting of the nonlinear term, so minus x to the third. And now we interpret x and y as elements in the phase plane. The phase plane is the plane, so we have x and y being two coordinates in R2, in which we can draw how x and y are changing over time. And we draw a phase plot. The idea is that you look at the phase plane, and at each point in this plot, you can compute the velocity of this point. And we draw an arrow in the right direction that scales with how fast you're going. So if we are at 0, 0, there is no arrow because our right-hand side is 0, and the further away we are from 0, 0, the faster we are going because both the y component and the x component are increasing the further away we are from 0. And if we keep picking points and drawing arrows, we'll fill R2 enough to be able to have an intuition of how things are going. So we can fill it with a lot of arrows and then pick a point, for example this red dot, and understand how the solution goes just by letting this point follow the arrows that we have already drawn. So something like this circle. And then if we fill a lot of things, we'll start finding full circles coming back to each other. It's true that when you're just looking at arrows, you might not really be sure that it reconnects, but that is what we have proven the previous time. It does reconnect, it's a periodic orbit. So now we have visualization of how the behavior of x and y is changing over time. Remember, x is our previous solution of the ODE, y it's the velocity of x. We can do something similar in harder cases. So let's look at this situation in which I just changed the sign of x to the third. We can do the same thing. We look at R2, that is x and y, with x being the unknown of our ODE and y being its first derivative, and we try to fill the plane with arrows indicating the velocity of the xy vector. This is called a quiver plot. Doing it by hand is usually a lot of effort, but computers are really good at doing these sort of things. So next to this video, I'm going to be posting a link to a very simple website that can help you, that draws quiver plots for you. You just have to insert the vector field. This is called a vector field. It's literally a field full of vectors. And if you insert the vector field, you'll get a quiver plot. But now let's concentrate again on this example. We have 3 points in which the right-hand side is 0 on both components. So those are the 3 dots I drew on the x-axis. And we can imagine that there are some sort of this connections can be drawn. There is always a little bit of guessing when you're looking at quiver plots. There might always be a little bit of unknown if things actually connect like this. You might have a little bit of wiggle room, but we can draw this, and with extra analysis we can prove that this is indeed the set of solutions we would have. So taking away the quiver plot, this is a representation of the solutions of our ODEs, in which on the x-plane you have the unknown of your full ODE, while on the y-plane you have its velocity. So here you notice that at the top you have something that has always a non-zero velocity, so it keeps changing. At the bottom the same, and then in the center you have a periodic solution again. And you have one solution that goes from a fixed point, a point that doesn't move, to another fixed point. You can also look at it from the physical interpretation perspective that we did before, so looking at a potential. We can write the potential in this case as well, and it looks very similar to the potential that we wrote before for the previous equation, except that we have a minus instead of a plus. And if you draw the potential in this case, you retrieve this fourth order parabola tending to minus infinity on both sides with a wiggle around zero. So you can see that the periodic solutions would be in that valley around x equal to 0, but if you have too much energy, you get over the valley. So if you started further left or further right with a certain velocity, you would be able to get over the bump and through it. This combines with the information we got from the quiver plot to understand that in the center, within the two maxima of the potential, we have indeed periodic solutions.